Hello everyone and welcome to chapter 8. In this chapter we're going to cover sections 1 through 4, which are going to cover 10 reactions on how to react alkenes. In our previous chapter we talked about how to create alkenes through elimination reactions, and so essentially now we're just doing the next step. So we're going to start by looking at our general reaction for this chapter. We're focusing on what we call addition reactions. So here's our alkene. We're going to react it with X and Y. So again, just being very generic here. And what's going to happen is we're going to add one of those atoms to one carbon of our alkene and the other atom to the other carbon of our alkene. And just a reminder, when we refer to our alkene carbons, the two carbons that are in that double bond are called the vinylic carbons. And so we'll use that word to describe where a reaction is happening or how it's happening. And so in these reactions, our vinylic carbons are each gaining a new atom, a new group, and the pi bond is going away. Now when we talked about our nucleophiles, we said that they have to have some amount of negative charge, and that can come from a pi bond. So here is our pi bond here acting as a nucleophile. We're doing a nucleophilic attack on that electrophile, and so we're using the pi bond electrons to create a bond from our vinylic carbon to that electrophile. So this bond right here is our brand new bond. The pi bond doesn't exist anymore because we reused those electrons. But as a result, the other vinylic carbon is now a carbocation because it lost its fourth bond. Now, our pi bond can also act as a base. And as I've talked about, a base is just a specific type of nucleophile. It's a nucleophile that bonds to hydrogens. And we know a lot of nucleophiles can act as bases, and pi bonds fit into that group as well. So here our pi bond is bonding to that hydrogen, and our vinylic carbon is forming that bond to the hydrogen, and then our second vinylic carbon is gaining that positive charge. We also always like to talk about how this connects to the real world, and so here's just a couple examples of alkenes that we would find in nature as well as in industry. So the flow chart here shows us how alkenes are made. And so at the top of our flow chart we have petroleum. And so petroleum is something that we find as a natural resource. And from that we can go through a cracking process to create ethylene and propylene. And then from those two small molecules we can make a huge amount of chemicals. So ethylene and propylene are very important starting materials in a lot of our industrial processes. And we say industrial and you might think, like an oil refinery or something big like that. But this means that they're going into any type of factory or any type of manufacturing plant. And then the other two molecules on the side, we have vitamin A, and so we see all the different alkenes that are part of that vitamin A molecule. And then alpha terpinyl, which is naturally occurring, and it smells really nice. And so even though it is found in sap and in tree bark, it's often used in flavoring and in cosmetics and in perfumes because of its nice natural smell. So as we go from a substrate that has a leaving group attached to it, and we have a beta hydrogen attached to it, we can react it with a base and we can create an alkene. That was part of chapter 7. What we're doing in this chapter though is taking that alkene and now reacting it with two atoms and creating this addition product. So these two processes are opposites from one another. And because they're opposites from one another and often in equilibrium with each other, we have to find a way to control the reaction so we get what we want. We can push that equilibrium in either way. And we're basing that off of our delta G equation down here. And again, we're not doing the math with it, but we are using the concept to help us explain how we would control the reaction. And I'm going to use my whiteboard here. Addition reaction, our delta H is going to be a negative value. It's going to be exothermic. We're creating new bonds, so it's going to be lower in energy because we're creating new bonds. The delta S is also going to be negative because we are going from having 2 molecules down to just 1 molecule. So our entropy is decreasing. And so in our equation, in the G equation, let me get back to our slide here, we know that our delta G is equal to delta H plus negative T delta S. In order for a reaction to be spontaneous, our delta G needs to be negative, or in order for it to favor the product would be the way to say it for what we're looking at now. So in order for our addition product, we would want to have our reaction at low temperatures. And for an elimination reaction, our delta H value is most likely going to be a positive number because we are creating a pi bond, but we're breaking multiple sigma bonds. And our delta S value will also be positive, which is a good thing because we are going from having multiple molecules. And in order for our reaction to favor an elimination side of our equilibrium, we would want to do this at high temperatures. And so this is based off of whether our H or our S are negative and how we can control that T value to give us our negative delta G. So we're not going to look at this based off of numbers, we're definitely looking at it based off of concepts. So knowing that addition reactions benefit from low temperatures and elimination reactions benefit from high temperatures is really the extent of how we're going to utilize that delta G. Okay, so this is one of the last pages of the chapter. It's page 390. And I'm starting with one of the last pages so I can show you how the reactions are organized. So in the center here we have an alkene, and we're using our arrows here to show the reagents and the product it's going to create. These are all numbered, so 1 through 10. And they're numbered down here to tell you their names. As I go through our reactions, I am also going to number them. I like their numbering system, and it's an easy way for us to talk about them. So I'm bringing this up so you know where the numbers are coming from and you have reference to them. Now within the chapter, they don't use these numbers to refer to them. They refer to them by their name. But within my notes, I use the numbers so then you can connect them to the textbook. So we are starting with reaction number 1. Now, I am going to make a little summary slide for reaction number 1. And I'm going to suggest that you guys start keeping a reaction notebook. And I mentioned this a little bit in the last video. I think I'm just going to make a separate video just for reaction notebooks to give you a better idea of what I mean. But you can see that the chat already has 10 reactions. So they're going to add up quickly as we go through our chapters. All right, reaction number 1. This is a hydrohalogenation reaction. Now, knowing the names is not important, but it is telling you what's happening. Hydrogen, halogen, some kind of halogen. So it means we're adding a hydrogen and a halogen to our alkene. So what I'm putting on my little whiteboard is what I would put on a big whiteboard if we were doing this in our classroom. So within this reaction, we're going to start with our alkene, and we're going to react it with a hydrogen with a halogen. So far this is what I've written down. Reacting it as HX, and my halogen can be chlorine or iodine. And then the looks like this. So on those two vicinal carbons, I'm going to add a hydrogen to one of them and my halogen to the other. And I like to put down just kind of the generic name of what we're creating. So we started alkene, and what we're making is a haloalkane. And then underneath it, I'm going to put some extra. So for this one, I'm going to label this as a Markovnikov reaction, which I know doesn't mean anything to you yet. Will. Markovnikov, make sure I spell that right. And then I'm also, when we talk about reactions, we like to talk about regioselectivity, so where things will add, and we like to talk about stereoselectivity. So Markovnikov is telling us about the regioselectivity. So it's telling me that my halogen added to this carbon and my hydrogen to this one, and not the other way around. And telling us that it's racemic means that if we are creating a stereocenter, a chiral center during this reaction, we won't get just one enantiomer. Now, to explain both of those pieces of information, we need to look at the mechanism. So we need to look at how the reaction occurred. So here is our mechanism. Here's our alkene. We know that our alkene is going to use those electrons, so we are using those to grab onto a hydrogen. Now, because we're using hydrogen here, the proton transfers, and our hydrogen can't bond to more than one thing at a time. So we're going to do this arrow as well to break the bond between the hydrogen and the halogen. Now when that happens, we're creating this new bond right here between the hydrogen and the carbon, and that means that our other vicinal carbon is now a carbocation. So then the second step of this reaction, we're doing a nucleophilic attack. So from our halogen, we're going to draw an arrow to that carbocation, and that creates a new bond to our other vicinal carbon. So Markovnikov's rule states that we're going to put our carbocation in the most stable position. So another way to think about that is that our hydrogen is going to go to the carbon with more hydrogens. So the hydrogen will add to the less substituted carbon, which allows for the carbocation to form on the more substituted carbon. That is Markovnikov's rule. So we use that rule to describe reactions. Hydrogen with the hydrogens, halogen, or whatever our nucleophile will be in future reactions, goes to our more substituted carbon. Now for stereochemistry, because we're creating this carbocation right here, when our adds to it, it can add to either side. This is a trigonal planar geometry, and so it can add to the top or the bottom equally, and so we end up with a equal mixture of both enantiomers if a chiral center forms. Now, because we are forming a carbocation in the middle of this reaction, we do have to keep an eye out for carbocation rearrangements. So all of those patterns that we've learned in our past chapters, again, they're not going away. So we form a carbocation in this reaction. We're doing our proton transfer, where our pi bond is grabbing onto the hydrogen, and our hydrogen-chlorine bond is breaking. So when we do that, our hydrogen is going to bond over here. Let me draw it in for us. Here's my new hydrogen. and we create the secondary carbocation right there. If we do a hydride shift, so we're going from the hydrogen on the next door neighbor and shifting it over, I'm going to draw on my original hydrogen here. We go from having a secondary carbocation to a tertiary carbocation. And remember, our shifts are only going to happen if it increases the stability of that carbocation. So down here is that original alkene that we started with. Our product over here with 60% is the product after it went through that 1,2 hydride shift, and the product with the 40% is the original one. So the one without the shift. If we are going through a shift, the major product will always be the one from the shift, and the minor product will be the one without the shift, but they will always both form. So I'm going to add one more piece of information to my little summary here, a little reminder that we form cation, so that reminds me that I need to look out for carbocation rearrangements. Everything that's on our list here is a good summary of that first reaction. So with that, we're going to go to our second reaction. So our second reaction looks similar. We're still working with an alkene, which is, the chapter, and we're still reacting it with HBr, but underneath the arrow there, we have ROOR. So this is a peroxide. And we're probably most familiar with hydrogen peroxide, which is H2O2. Because this has R's on it, that tells us that we don't really care what type of peroxide it is. We just need it to be some alkyl peroxide. So reaction number 2 is a hydrohalogenation. So I still am starting with my alkene, and I'm going to be reacting it with HBr, and this time Br is the only halogen that we can use, ROOR, and this is our peroxide, so it looks like this. An oxygen-oxygen single bond is not very stable, so that we're going to make from this is a bromoalkane. So I can't say haloalkane because bromo is the only one that can go through this pathway. I can label it as a bromoalkane. Now, what is very different about this one, notice that my bromine went to the carbon. So we say that this is an anti-Markovnikov reaction. And so that tells us that our halogen is going to less substituted position and our go to the more substituted. The mechanism for this one is quite a bit different than reactions that are in this chapter, so we don't actually talk about it. So I'm going to write down that there's no mechanism for this one. It's actually something that we'll talk about in chapter 10. So we will get to it. Our book likes to group mechanisms together based off of similar reactions, just doesn't fit in with the rest of this chapter. All right, we're going to do one more practice problem, and then we are done. I think this is my last slide. Yes, it sure was. Okay, so let me erase this. Oh, so this is our summary then for reaction number 2. And again, it would be racemic. We'll add that piece of information here so we know our regio and our stereo. Okay. Now, how I like to practice these is I do what I call box problems. So I lay out some type of information. So usually when we're just starting the practicing, I will have the reactant and the reagent, but the product will be missing. Now, because our tests are, of course, are going to be different for our semester, I'm not sure how the test will look right now, but this is generally how I like to do them. I don't think my boxes are actually going to be big enough for what I'm going to draw today, but this is our idea. So we're starting with that alkene in the middle, and we want to know what would form if we react it with either of those sets of reagents. So let's start with the one on the left, the one that we just learned. We know that we're going to add a hydrogen to one of our vicinal carbons and a bromine to the other one. And we know that this is going to be anti-Markovnikov, which means that we're going to add to our less substituted carbon. So there's my carbon chain. That part didn't change. Here's my hydrogen adding to the more substituted side, and there's my bromine on the less substituted side. Now, I don't have to draw hydrogen, but of course it does help us to see what's happening. All right, now over here, we know that our hydrogen to our less substituted side, so this one is our Markovnikov rule. So after that first step, we're going to form that. Now that is a secondary carbocation. And right next to it, we have a carbon with a substituent. So we know that if we do this hydride shift, we can have a tertiary carbocation. So our chlorine is going to add to both of these. So my products, and I'm going to add my original hydrogens back in here as well. This will be my product without rearrangement. And this is my product with rearrangement. And then what we talked about with this is if a carbocation rearrangement can occur, then that means that this is my major product and that's my minor product. So those are my two final answers for that reaction, my HCl reaction. All right, that is it for our first video for Chapter 8.